So I have alluded, but not really said specifically, about directions and how crystals are oriented. And this is actually super important depending on what kind of material you're using. So let's see, I've got to find this other thing again because I closed it. I hope you don't need to send me a Duo thing again. No, you don't. Good. Thank you. I have a bad habit of talking to electronic things, and they don't ever talk back, which is probably good, because if they did, I can't use those things like Alexa and stuff because they never understand what I'm saying, and I get frustrated. Siri is the same way. I say it one thing, and it just like doesn't at all understand. So I guess I am finally too old for something technological. I didn't think I would ever get that way, but I evidently am, because voice activation does not work for me. Anyway, we're going to talk now about how you figure out how the particular crystal is oriented. And it actually is really important how it's oriented. I do have a bigger structure, crystal structure thing. I didn't actually bring it with me. I will bring it later, but not today. But crystals need to be classified, and they need to be classified and oriented so that when they get cut up, like in slices like that, we know kind of what the structure is at the surface and what the atomic structure is. So if you have an atomic structure, and silicon is like, it looks different depending on what way you're looking. So it's not really a square or a cube. You can turn it one way, it looks one way. You turn it another way, it looks another way. So we need to know what we're looking at. So crystals form repeating patterns, which hopefully they would because they're crystals, which is good. So the first thing we need to talk about before we talk about how to figure out where and how the crystal is oriented, we need to talk about lattices. Most people know what a lattice is. If you have one of those crossy things under your deck, that's a lattice. It's just basically a periodic arrangement of things. We call a periodic arrangement of atoms a lattice. And atoms can get arranged in all kinds of different ways, depending on what the structure is. Atomic arrays, or lattice crystals, are represented by lattice points. So a lattice point basically tells us what the geometry of the structure is, and then something called the basis is actually the atoms or molecules that go into it. So there's actually, the points that I'm going to be talking about are not atoms, they're just points in space that are saying where something might be. So let's say, and I don't want to go into 3 dimensions, so it's because it's a pain, so I'm sticking with 2 dimensions, but you can imagine this works in 3. Let's say we have a regular array of some type of structure. So this is just a 2-dimensional array of dots. We can pick a point, and we can go in 2 directions that are not the same direction, and we can get a kind of a shape. So we take it, we go 2 points, and we get this shape, A. And this is called a unit cell, because we can repeat this over and over and over again and get that original structure. So if we took A and we just kept moving it and kept repeating and kept building it out, we would get that lattice structure. They're actually, you can imagine perhaps, because I'm not going to do it, but you can imagine that if I extended this out of the page or into the, I can't say the board because we don't have boards anymore, but into the screen, that would be the 3rd dimension, and we could add a 3rd dimension. It doesn't have to be perpendicular to the other 2, it's just another direction. So we could do that, but we're not going to because it's just too difficult to draw. That's not the only unit cell for this particular lattice that exists. There's lots of them. We can make all kinds of unit cells. Some of them are really simple, and some of them are not. A primitive unit cell is the smallest repeatable volume. So in this case, B would be the primitive unit cell, because it's the smallest thing you can make and repeat. It's not necessarily the easiest thing to work with, but it is the smallest. So we can repeat any one of these and get the same structure. So any one of these can kind of move around and be recreated, and that's what we use unit cells for. However, and we'll look at kind of structures. If we look in 3 dimensions, we can get a 3-dimensional unit cell, and any 3-dimensional cell that is some kind of cuboid, that would be a unit cell. It's characterized by 3 vectors. Don't worry, you're not going to have to deal so much with vectors, just a little bit, not too much. And they don't have to be perpendicular. They don't have to be equal in length. They just have to be orthogonal, and that's it. You can get equivalent lattice points by just multiplying each one of the vectors by a constant, and that'll move it all over the place. And again, I'm never going to make you calculate that, so don't stress about that particular thing. I've had students get all stressed about that. You don't have to do that. Now, why are you doing that? Oh, I don't know. Okay, fine, whatever. Sorry, this is not cooperating with me. All right, the easiest thing to do is to use cubic unit cells, because cubic unit cells are cubes, and cubes are really easy to deal with. However, cubes don't always just have 4 or 8 or however many that would be 1, 2, 3, 4, 5, 6, 8. They don't always have just 8 atoms on each corner and that's it. A cube may contain more atoms than just the corners. So they're not always primitive, but they are usually the easiest thing to deal with. So there's 3 basic cubic types, and each one of them is a little bit different, and each one of them contains both the geometry and the lattice structure. So first of all, we're going to look at the simple cubic. A simple cubic is the simplest cubic unit cell you can have. And it's really, really, really rare. In fact, there's only one element that makes this naturally, and that's polonium. Oh, I have other stuff. Let's bring that up too. One of the really, really awesome people one of my mechanical students made me unit cells. And the weird thing about looking at this, you notice that there's 8 atoms. But for the unit cell, each one of those corners only contributes an 1/8, because each unit cell has to be repeatable, so you're not going to repeat all those corners. So really it looks like that. And the side of it is the length of the unit cell, whatever it may be. And each one of those atoms on the corner contributes 1/8. So the total number of atoms contained in this unit cell is 1. Because there's 1 on each corner, each one contributes an 1/8, and we get 1 atom. So this is a simple unit cell and not overwhelmingly useful, because it really doesn't appear much in nature. It's just it's really because of the empty space in the middle. If you have 4 atoms here and 4 atoms here and a bunch of space, it'll just tend to twist and collapse on itself. So that's why it doesn't occur very much. The next kind is more common, and that's known as a body-centered cubic. The only difference is there's a big atom in the center, and that makes it much, much more common in nature. Lithium, sodium, potassium, iron, they all make body-centered cubics, for which I also have an awesome model. A body-centered cubic, again, we only count the corners as an 1/8, but that 1 atom in the middle is counted as 1 atom. So when we go through and figure out how many atoms we have for that, we have each one of the corners contributing an 1/8, so that gives us 1 atom, and then 1 big old atom in the middle gives us 2. So the body-centered cubic contains twice as many atoms as the simple. And the last cubic, the last simple one we're going to look at is called a face-centered cubic. And a face-centered cubic has atoms on each face and atoms on each corner. So when we look at it, it looks kind of like that. A face atom contributes a half. Half of it's inside the unit cell and half of it's in the next unit cell. So if we're figuring out how many atoms it has, we have 8 corners, which gives us 1 atom. And then we have 6 faces, which gives us 3 more. So we get 4 out of that. So wouldn't it be nice if semiconductor materials made simple unit cells like that? They don't. They make a somewhat more complicated unit cell, which we're going to look at now, for which I also have a model. I gave my glass model to our new dean, but I still have the plastic model, which I like better. I don't like sending glass around the particular, classroom. That's where I am. Anyway, this is what the unit cell for semiconductor material looks like. And it is a little bit easier to see if you actually have it in 3 dimensions, because it's really, really hard to draw. It has, if you look at it and turn it around, you'll see that it looks different depending on what side you look at. If you look at it from the top, if you look at it from an angle, if you look at it from the middle or the edge, they all look different depending on what way you're looking at it. So this is known as a diamond structure, and this is what silicon and germanium make. I'll explain in a minute. Silicon and germanium make a diamond structure. Carbon also makes a diamond structure, but we don't use carbon. But carbon does make a diamond structure as well, sometimes, not all the time. And in this case, we have 8 corners. We have 6 face atoms and 4 all the way inside the structure, which is much easier to see if you're looking at a physical model than it is looking at it on paper. So that means the number of atoms we have in here are actually 8. We have 8 corners for 1, we have 6 faces for 3, and then 4 all the way inside. So we get 8 atoms in a unit cell. Gallium arsenide makes an almost the same kind of structure, but it's called a zinc blend. It is exactly the same, except it contains 2 types of atoms. So you'll notice that there are 2 different colors to the atoms here, and that's because one of the types is gallium and one is germanium. So the gallium atoms are blue and the arsenic atoms are green, and there are 4 of each in each unit cell. So you might see a unit cell where all the arsenic are all around the corners and stuff, or you could see it the other way. Either way would be pretty much the same. So those are the unit cells, and when we actually make it, I have a bigger model of actual silicon when it gets put into a structure, but I'm not going to do that today. So when we have, especially when you're looking at the silicon unit cell, you see that depending on how it's oriented, it has a different number of atoms that you're actually looking at. So it doesn't look the same from every angle. So semiconductors are basically fabricated. You notice we cut up those wafers into thin slices, and then everything that's done on them is etched onto the surface. So because of that, it's really important to know what's at the surface of the semiconductor material and how it's structured. So surfaces or planes can be cut through the unit cell in different directions, and we actually have a specific way of classifying those directions and those planes. Planes are classified by something known as the Miller index. The Miller index tells us how the plane intersects with the X, Y, and Z axis. That's basically all it tells us. It slices through the unit cell, it intersects in a certain way, and we just say, okay, it intersects X here, it intersects Y, and it intersects Z. If a plane intersects at, say, X equals A and Y equals B and Z equals C, we always invert those three numbers, put them in round parentheses, and that's the Miller index of that particular plane. So if an axis doesn't intersect, which sometimes it does, sometimes it is parallel to an axis, then that gets a value of 0 when because it's infinity and we intersect it. So a single plane is represented by parentheses. A family of planes, which is just a whole bunch of them put together, has regular brackets. That's just a collection of parallel planes. So you might see that on something that I talk about later, and that's all it means. The planes have a round brackets, and if I make them squiggly brackets, that just means a whole bunch of them. So let's look at what this looks like, because a picture is worth way more words than I could possibly utter. This is the outline of a unit cell. The lattice constant is how long it is from one end to the other. And a lot of times we just basically call that 1 because it's a unit cell. It does have a distance, it has a length. But we basically say that that point, like where plus x intersects with the plane, we just call that 1. So it goes from each one of those axes goes from 0 to 1. So if we were to look at this plane, this intersects at x equals 1. It does not intersect the y-axis and it does not intersect the z-axis. It's parallel to both of those. So the Miller index of that plane is going to be 1 over 1, 1 over infinity, 1 over infinity, which is 1, 0, 0. That's an easy one. That's a really easy one. If we intersect a little differently and we slice actually through the top at an angle, it intersects differently. So this time it intersects at x equals 1 and y equals 1. So the Miller index is 1 over 1, 1 over 1, and z doesn't intersect, so it's 1 over infinity, and we get 1, 1, 0. That's the 1, 1, 0 plane of the unit cell. We can also have a plane that intersects each one of these at 1, so we can actually intersect at x equals 1, y equals 1, z equals 1. And when we do that, the Miller index is just 1, 1, 1. The 1, 0, 0 plane and the 1, 1, 1 plane are the most important planes in silicon structures. Most semiconductor devices are made out of the faces of either 1, 0, 0 or 1, 1, 1, depending, and I'll talk about that later. I always tell you I'm going to talk about stuff later, but I will, but just not today, just way later. Those are the three simple planes. Those are the ones that actually are used frequently. There are others. We could have a plane that just sliced through and happened to intersect at these two really odd points. And we can't solve this the way the axes are put because none of the axes actually intersect with this. So what we have to do is we have to actually move the axes to figure out what the value of this plane is. So what is that word? This is what happens to me. What is I don't know. I have no idea what the word I'm thinking of is. But anyway, the process that we have to use is we have to get the axes so that each one of them is either parallel to or intersects this plane. So we can move the x-axis, say, up here. Now, if we do that, then it's at least closer to the plane. We can move the y-axis and the z-axis as well. The only problem is now x and z are way off the page. So what we do is we turn them around and make them negative. So they end up being negative axes. And now you can see where they actually intersect the plane. And we have x intersecting at now negative 1/3 because we always assume the place the three axes meet is 0. The Y-axis doesn't intersect, it's still in parallel, and then the z-axis intersects at -1/2. So then we flip all those over, and we get a Miller index of 3 bar, 0, 2 bar. The bar over it tells us it's a negative number. If you put a negative in front of your number, I won't care. It's just the standard convention is to put the bar over it, and that tells whoever's looking at it that that's a negative plane. There are also sometimes some planes that have more than one indicator. There are some where you look at it and you can move the axes up here or down here and you'll get opposite signs, but they're really the same plane. So those are planes. They take practice. On D2L, under Chapter 1, sort of way down at the bottom, there's something that says online practice finding Miller indices. It's basically a website which usually works, where it gives you 6 cubes with planes, and it's a multiple choice thing so that if you can get a couple of them, you can figure the rest out, and you just basically put your guess in each slot and it tells you if you did it right. And you can just do it over and over again, and it's a really good way to practice getting Miller indices to work. There will definitely be Miller indices on your first test and on the final, and you will definitely have to know how to find them, and they won't be 100 or 111 or anything super simple. They'll be more like the last one. So those are planes. The only other thing that I'm going to tell you about today, because I've told you plenty, are directions. Directions are just perpendicular to planes. So basically any direction is just coming out of whatever plane it's associated with. Directions are given square brackets. Family of directions are given triangular brackets, but those are just parallel directions. So this is a 100 plane, so that big arrow is pointing in the 100 direction. Basically just perpendicular to the plane. The 110 direction comes out of that plane. The 111 direction comes out of there. And then the last one we did was the 302 with the overbars, just comes straight out of that. It's really hard to make a slide make it look exactly like it's perpendicular, but it's supposed to be. So the directions are always just perpendicular to the planes and coming out of them. These become important when we start talking about crystal structures, and we need to orient the crystal in a certain way, and when we cut it, we need to orient it depending on what type of device is made. We're going to talk more about how that process is done later. I have told you plenty for today.